This is Unit 4, Chapter 15, Section 15.7, Triple Integrals in Cylindrical Coordinates. So in plane geometry, the polar coordinate system is used to give a convenient description of certain curves and regions. Figure 1 will help us to recall the connection between polar and Cartesian coordinates. We know that if P has Cartesian coordinates x, y, and polar coordinates r, theta, we have then that x is equal to r cosine theta, y is equal to r sine theta, r squared is equal to x squared plus y squared, and then tangent theta is equal to y over x. In 3 dimensions, there is a coordinate system that we're going to call cylindrical coordinates that is similar to polar coordinates and gives convenient descriptions of some commonly occurring surfaces and solids. As we will see, some triple integrals are much easier to evaluate in cylindrical coordinates. So in the cylindrical coordinate system, a point P in 3-dimensional space is represented by the ordered triple P of r, theta, z, where r and theta are polar coordinates of the projection of the point P onto the xy plane, and z is then the directed distance from the xy plane to point P, as shown in Figure 2. To convert from cylindrical to rectangular coordinates, we are going to use the equations. Again, x is going to be r cosine theta, y will be r sine theta, and z will just be defined as z. Whereas to convert from rectangular to cylindrical, we're going to use that r squared is equal to x squared plus y squared, or tangent theta will be y over x, and again, then z equals z. So let's take a look at example 1. We're going to plot the point with cylindrical coordinates 2 pi over 3, 1, and then find its rectangular coordinates. And then for part B, we're going to find the cylindrical coordinates with rectangular coordinates 3, negative 3, 7. So to plot the point, we're going to move out as a radius unit 2 around from the positive x-axis. So visualize this axis, and we're going to move to angle of 2 pi over 3, and then we will go up 1 point, 1 unit to z. From the equations given previously, its x-coordinates are going to be x is equal to 2 cosine of 2 pi over 3, which gives us 2 times negative 1/2, or negative 1. Y will be 2 sine 2 pi over 3, which is 2 times root 3 over 2, which will be the square root of 3, and z will equal 1. So then our coordinate points are going to be 1, square root of 3, 1. Or I'm sorry, negative 1, square root of 3, 1. For part B, we're looking for the polar or the cylindrical coordinates. So we know then that r is going to be the square root of 3 squared plus negative 3 squared, which will then be 3 square root of 2. We know that tangent theta will be y over x, so negative 3 over 3, which is equal to 1. And that gives us theta is equal to 7 pi over 4 plus 2n pi. And then we have that z equals 7. So we will have then one set of cylindrical coordinates would be 3 root 2 and 7 pi over 4 and 7, or we could also have 3 root 2, negative pi over 4, and negative 7. So as with polar coordinates, there are going to be an infinite number of possible choices. Now, to evaluate triple integrals with cylindrical coordinates, we're going to suppose that E is a type 1 region whose projection D onto the xy plane is conveniently described in polar coordinates as shown in figure 6. In particular, we're going to suppose that F is continuous and E is going to be defined as all points x, y, and z such that x and y are contained in D, and u1 of xy and u2 of xy are upper bound and lower bound of z. And D is going to be given in polar coordinates by all points r theta, such that theta is between alpha and beta, and r is bound by h1 of theta and h2 of theta. And therefore, we know from our study of triple integrals that our triple integral over the region E of our function f of x, y, z dv can be defined as the double integral over the region D of our single integral with bounds of u2 of xy and u1 of xy, f of x, y, z, dz, and dA. But we also have the ability to evaluate that double integral in polar coordinates, which would then be the integral from a to b, alpha to beta, and h1 of theta to h2 of theta, and then our interval u1 of r cosine theta, r sine theta, and u2 of r cosine theta, r sine theta, for our function f of x, f of r cosine theta, r sine theta, z, r dz, dr, d theta. This is the formula for triple integration in cylindrical coordinates. So we have the equation as shown for evaluating triple integrals in cylindrical coordinates, which says that if we convert a triple integral from rectangular to cylindrical coordinates by writing x equals r cosine theta, y equals r sine theta, and leaving z as it is, we'll use appropriate limits of integration for z, r, and theta, and we'll replace dv by r dz, dr, d theta. And figure 7 shows how to remember how to do this. It is worthwhile to use this formula when E is a solid region easily described in cylindrical coordinates, especially when the function f of x, y, and z involves the expression x squared plus y squared. So let's go ahead and take a look at an example. So we have a solid E that lies within the cylinder x squared plus y squared equals 1, below the plane z equals 4, and above the paraboloid z equals 1 minus x squared minus y squared, as shown in figure 8. The density at any point is proportional to its distance from the axis of the cylinder. We want to find the mass of E. So in cylindrical coordinates, we know then that r is equal to 1. The paraboloid is z equals then 1 minus r squared. And so we can define our region E as all points r, theta, z, such that theta is between 0 and 2 pi, r is between 0 and 1, and z is going to be between 1 minus r squared and 4. And since the density is going to be proportional to the distance from the z-axis, our function, f of x, y, z, is equal to a proportionality constant times the distance, which is going to be x squared plus y squared, and converting that to polar is just kr. Therefore, we can set up our integral where the mass is going to be the triple integral over the region E of k times the square root of x squared plus y squared, which is our function, dv, which is going to be the integral from 0 to 2 pi, the integral from 0 to 1, integral from 1 minus r squared to 4 of kr, need the r, and then dz, dr, and d theta. And I will leave the solution of that to your video, to your questions at the end of the video.